Please listen carefully.
Hello and welcome to GasGasGas, your one-stop podcast for the FRCA primary exam. This podcast will fill your brain with information. Listen to it, think about it, and check out the show notes on the website. There you will find the core diagrams you need to be able to draw and describe for the exam. This podcast can squeeze into your day. Listen while you're driving to work, cooking dinner, maybe when you're on call, or in the gym. Eventually the revision is going to end. But for now, expect facts, concepts, model answers, and the odd tangent. Remember to rate and follow the show to hear much. Hello, my fellow GasGasGas compatriots. Today we're going to talk about pKa. This is an important pharmaceutical concept that I've mentioned in brief in the fentanyl podcast, alluding to how drugs get across membranes. To be a bit more specific about pKa, it is a number used to reflect the balance or the ratio of ionized versus unionized molecules of a drug that are floating around in a physiological system. As with fentanyl, the reason why we care about this number is because only the unionized portion of a drug can cross membranes. And you may be shocked and surprised to discover that most drug receptors are not inside the endothelium of your arteries, but they are in fact on cells. Therefore, drugs have to get across membranes to get to the cell membranes themselves in order to exert their effect. Ionized molecules cannot cross these membranes, bearing in mind that these membranes are fairly resilient to positively charged molecules crossing them. To think about pKa in a little greater detail again, the number you get, often it's 7.3 or 8.1, etc., is the pH at which that particular drug is in a 50-50 ratio between ionized and unionized particles, or charged and not particularly charged particles. So you could imagine that a drug with a pKa of a physiological pH, let's call that 7.4, would have 50% of its drug molecules floating around in the plasma ionized and 50% of those molecules floating around unionized. That 50% wodge of unionized molecules can dive across membranes and have an excellent time. Remember, going back to the depths of your knowledge with chemistry, most acids within a system balance in ionized and unionized states, as do those basic molecules, and the nature of that system can sometimes influence the ratio of ionized to unionized or associated versus disassociated molecules. That's where we're sort of coming from and how you should be thinking about pKa. It can sometimes also be described as the lipid partition coefficient. Probably a bit more of a complicated term, not one that comes up in the syllabus in quite the same way. So we've covered heavily the fact that this is the number at which a drug is at ratio ionized. If you had a drug that had a pKa of 8.1, then if you put that into a human with a pH of 7.4, the ratio would swing a fair way in the opposite direction. For example, levobupivacaine has a pKa of 8.1, so actually only 15% of it is unionized at a physiological pH, i.e. there's not much of it to start with that could work on a neuron. So just to break down the actual term pKa, because breaking things down can actually help you remember stuff, there are 3 letters and they all mean a different thing. So your P, as in pH or pKa, P reflects logarithmic numbers, in this case a negative log. K is actually the coefficient. It's a K, not a C, because I think the person who originally postulated this concept did so in a Germanic paper, and therefore constant is spelled with a K. Just to confuse you, it's a capital K, which is important to note, because there are some lowercase k's lurking around the place as well. And then the A, subscripted, the A bit of the Ka value refers to acids, and refers to acids, particularly the dissociation constant of that acid, which again is something that is probably in the depths of your mind from chemistry A level. Ultimately, this number reflects the propensity for an acid to dissociate. So if we're thinking hydrogen chloride, that's a molecule in itself in a non-dissolved form, but when it's added to a watery environment like a beaker or a human, the hydrogen and the chloride dissociate to a negatively charged chloride ion, and your positively charged hydrogen, i.e. proton, i.e. the acidic bit. Ka refers to the propensity for that equilibrium to shift towards very large numbers of hydrogen ions and chloride ions against its original hydrogen chloride molecule, because they're in a balanced equilibrium. Not going to do too deep a dive on this because eventually we'll have to do a long conversation about Henderson-Hasselbalch equation and all those acid-basey type exciting things. But today is not that day. Instead, we're going to think further about pKa. Particularly, there are some rules of thumb, and these you could use and apply to a situation to get an idea of the likelihood for things to break apart or join together. Bases, i.e. basic molecules, tend to be ionized below their pKa, whereas an acidic molecule tends to ionize above their pKa. Now, I don't know about you, but that really confuses the heck out of me, because it implies that you have to know if a drug is acidic or basic, which is like loads of thinking, and is perhaps over the top, really. But to think about it a step further, acids and bases, depending on their solution they're dissolved in, will reflect their ability to either be more water soluble or more lipid soluble. And that's really what we're interested in, because water soluble things tend to get stuck in the plasma, whereas lipid soluble things tend to have a delightful journey off into the nether regions of brain, spinal cord, and all in between. So a weakly acidic drug is more lipid soluble, i.e. happier to get across membranes, in an acidic solution. So weak acids in acidic places go places. Equally, a weak base in a alkaline place likes to go places. So weak acid and bases in their respective acidic or basic environments are nice and lipid soluble. Whereas if you plonk an acid into an alkaline solution, i.e. put the situation contrary, they get stuck in the water, they don't really venture forth. And the same, a weak base plonked in an acidic solution becomes less lipid soluble. So the important thing to take is an acidic drug in an acidic place gets around, and a basic drug in a basic place gets around. When I was initially studying for the primary FRCA, I certainly started to get pH and pKa and Ka and disassociation, association, everything all very muddled up in my brain. So it's important to write all these things down, try and read about it. Peck and Hill is good in order to try and get it organised in your noodle. Boringly or troublingly or delightfully, depending on your perspective, knowing the pKa's of many drugs is also boringly important and something that may come up in the exam. It's particularly thought about with local anaesthetic drugs, opiates, and general anaesthetic induction agents. I'm not going to list a bunch of numbers at you because it's kind of pointless and painful. You got to go learn that yourself, but you'll really enjoy that, won't you? An example that's often touted to try and describe pKa, and it might come up in an exam or in some other teaching, so having an idea about it is useful, is that of aspirin. So the pKa of aspirin is 4.4, and therefore, in your nice acidic stomach acid, when you've taken your 300 milligrams of aspirin for your migraine, you might take 900, that's also a legit dose, is going to lead to quite a lot of unionized aspirin in your stomach, floating around, being super duper keen to get across membranes. And you would have thought, oh wow, that means that it's absorbed almost entirely through your stomach. Unfortunately, you'd be wrong, because the surface area is so pants relative to the small intestine. As it shifts over into the small intestine, which has a higher pH, i.e. is more alkaline, the surface area is greater, and therefore, despite there being a lower rate of unionized molecule, more molecule gets across into your plasma and off to other parts of your body, because there's more surface area. So it's important to bear in mind that there are other factors that influence how much drug gets to where it's going to go, not just the pKa. So well done for listening. I've not included a "Dear Doctor, please describe pKa" section today for this one, because it just seems like this is quite a small singular concept that you just need to grasp thoroughly. So just to go back over that again, pKa is a number. And it is a number that reflects the ratio of unionized and ionized drug in a system, i.e. a human. It is the number at which there would be a 50-50 ratio. So just going back to our dear bupivacaine, pKa 8.1. If you put it in a solution that had a pH of 8.1, you'd have 50-50 ratio of ionised and unionised. Fortunately, you squirt it into a human being instead. You've squirted it around their brachial plexus. Unfortunately, although I've not measured it myself, I imagine the pH of someone's brachial plexus is more like 7.4, therefore only 15% of that molecule disassociates, associates, rebalances, however you want to think about it, into unionized drug that can cross the neuronal membrane and act on those sodium channels on the inside of the nerve. Cool. Well, thanks for listening. I hope you enjoyed today. Next up, it's going to be clearance, but particularly hepatic clearance, because it's a bit more interesting and it really confused me when I thought about it. See you next time. Thank you very much. Dr. Gas out. If you found it useful or awful, please like and subscribe and rate the show. Definitely check out the show notes for those diagrams and the detail of this content. It is a bucket of content to get to grips with. Keep working at it, and you will get better, faster, and stronger. It is vital to keep your interest live for the science that we're covering and not overcook yourself. You will be amazed by what you know come exam day. Don't freak out. Keep studying.